Hi everyone, we're with Professor Stephen Williams at Southern Technical College. We are about to review Chapter 3, which is Motor Transformers and Distribution Systems for the Motor Controls class.
Okay, my attempt here, number one, is to do a review of the chapter. Okay, this is Chapter 3, planning to do several chapters in preparation for a midterm exam. My objective is also to pinpoint those things that are important to you and those things that are not necessarily important to you. It depends upon your frame of mind, so to speak. For example, in a residential setting, a lot of this is not important. In an industrial setting, quite a bit of it's going to be important. So I'm going to take the latter route, figuring that you're not going to stay in residential forever, or that you may just find yourself in industrial, who knows what. So industrial commercial is more in tune with what we're dealing with here. All right, but it gives you a general overall feel of what the subject is. Now in this case, transformers and distribution systems, some pretty important things to remember here, and we're going to flip through the chapter as we go. Okay, and the first thing it talks about is power distribution systems. You need to keep in mind that there's levels of distribution. First level we're going to talk about is transmission. All right, transmission is basically from the power producer, the power plant, to the end users. Okay, in between they have distribution, but you're looking at basically a system of high voltage poles. They could range from anywhere, I've seen them 100,000 volts up to, I know in here they talk about 750,000 volts. I have not personally seen that. I've seen the 500,000. However, with that in mind, you're looking at a high voltage system. Okay, the first thing you need to realize is there's a reason why it's high voltage. If you think about it, you're transmitting power. Well, power is volts times amps. Okay, so the higher the voltage, the lower the current. The lower the current, the lower the losses. Okay, so there's a pretty big benefit to keeping it high voltage. Of course, there's a cost also. You have to take up more room. You have to separate the voltages. As I said, a rule of thumb in separating voltages, and this is a conservative rule of thumb, is if you maintain a separation of 1 inch per 1,000 volts, that's good. You're always going to be on the safe side. Okay, so if I am dealing with 1,000 volts, 1 inch of separation is sufficient that it won't jump the gap between two different conductors. All right, and if I had 10,000 volts, 10 inches, 100,000 volts, 100 inches. So 120 inches is 10 feet. Well, you remember in here they tell you 10 feet. Well, that's good enough for, and again, conservative estimate, 120,000 volts. Realistically, you can probably get away with a little less, but if you maintain that separation, you're always going to be good. So the key is to know the voltage that you're dealing with, which is easier said than done. A lot of it can be determined by looking at the size of the insulators. The longer the insulators, the higher the voltage. In other words, that's a separation they're maintaining between, for example, phase to phase and phase to ground. Now, phase to phase is going to be a larger separation than phase to ground, because typically, unless you're dealing with a delta system, which is not normally the case. Normally you're dealing with what they call a Y connected three-phase system and a Y connected three-phase system, the phase-to-phase voltage is always the total voltage, and the phase to ground is that that phase voltage divided by the square root of 3. So therefore, as far as ground is concerned, you can maintain a little shorter distance. Again, that's based on the fact that you've got 3 poles, each of which is separated by 120 degrees. So as one's changing, the other one is changing 120 degrees out of phase, and the next one's 120 degrees out of phase with that. Ultimately, if you put them all together, they cancel out each other. Okay, but so much for that. So you can understand then when you're transmitting power, which is what we're trying to do here, the higher the voltage, the lower the current, VI. Okay, so they're inversely proportional to one another. One goes up, the other one goes down. So with that in mind, the higher the voltage, the less the loss. Okay, so what are losses? First off, you've got VI, which is voltage drop. I'm sorry, IR, which is voltage drop. So V equals I times R. All right, so that's important because now if you cut your current in half, you also cut your voltage drop in half. All right, now the other type of loss is power loss directly in the form of heat. Okay, and that is I squared times R. So just looking at that relationship, if you've got a square function and if you half the current, you've cut the loss associated with it by 25%. So you've cut it by 75% when you just cut the current in half. So doubling the voltage goes a big way to eliminating, well, you can never eliminate losses, but minimizing the losses. It's a trade-off when it comes to, again, the type of poles, for example, that you're going to have to put in to be able to support this as it's transmitting through miles and miles of territory. All right, so that's the major thing. Now, when you come down, and we're looking here at page 2. Okay, there's a little diagram there. Very rudimentary, so to speak. You've got a power plant. You've got a main unit transformer that's stepping it from whatever the 20,000 volts up to 345,000 volts. That's quite frankly the voltage we used to transmit up in Michigan, and it's not uncommon throughout the country. Okay, and you've got large poles that are supporting it, and as you go along you come to a point where you need to step down that 345 kV to some type of a lower voltage. In this case they're showing it as 4,000 volts. Now when you step it down there, you do so through what they call a unit transformer or a substation. A substation is, again, where you're taking a large amount of power and stepping it down from the transmission voltage down to perhaps a sub-transmission voltage. Okay, and we'll talk about those different numbers a little bit later on. And when you get to a sub-transmission, okay, you are still considered transmitting. Okay, but you're not yet into the distribution levels. Distribution levels usually start about 30,000 volts. All right, and now what you're looking at is you came to a town along your route. You know, you've got these big, long power lines that stretch for hundreds of miles, and you're passing a town along the way. So obviously that town wants some power, but they can't really use 345,000 volts. But they could use nice little 110 and 220, and maybe there's a commercial and an industrial spot there that needs some 480. So again, even though we're stepping it down, we don't want to step it down too far, because you may be going miles and miles through that town, okay, depending upon how big it is, how densely populated it is. So you step it down, again, it's a trade-off, because the more times you step it down, the more hardware you're using, the bigger the transformer, okay, and some transformers are quite expensive. All right, so we go down into a unit substation. Now let's suppose this is for an industrial site, all right, and you'll notice that on the next page over, we've got what a unit substation would actually look like. Now, the first one is called the primary switch. Well, what is that? Okay, well, you need a place where you can remotely remove that substation from service. Let's suppose there was a major storm went through, like a hurricane, and it hit, or a tornado, and it hit this particular area real hard, and it knocked out a bunch of power in the area. Well, the power grid might prefer to have that whole substation shut down. All right, so what do? They can remotely push a button and they can open that primary switch. All right, so it's a big breaker, and the size of that breaker is dependent upon the voltage level. All right, so if I'm dealing with a 345,000, okay, that is not, what you're seeing there is not going to work. All right, if you picture that as being about 8 foot tall, no, not going to work. All right, the breakers for that level are huge. Okay, huge being, they can be, oh, it depends upon what kind they are. I've seen, the trend seems to be to go to vacuum breakers. Why? Because number one, if you are breaking a set of contacts, making or breaking a set of contacts in a vacuum, you have no arc. So that's one of the biggest problems associated with making and breaking contacts, is the arcing that's involved. When it's exposed in air, you basically end up arcing as you're pulling them apart and bringing them back together. All right, so to eliminate that arcing, they go with vacuum breakers, where they're making and breaking that arc within a vacuum. Some of them are gas, where you're using gas to quench the arc. Many different types. All right, so anyhow, if we're going back to the substation, the first one is going to make and break that high voltage. Okay, typically it's going to be a one position. Okay, meaning that you only need one of those high voltage breakers to be able to interrupt it. All right, then you've got a transformer that's converting that power. In this case, obviously not a high voltage or 345 kV transformer. If it was, it would be probably 4 times as high as that one, and have insulators on top of it that are probably up to about 20 feet long. All right, so yeah, you're not going to fit that in a little thing. So that's another reason why, for example, they use sub-transmission. Because if I have a number of industrial sites in an area, for example, maybe I'll take it down to, say, 100,000 volts, all right? And now, okay, I've just basically cut the size of my transformer down tremendously, to the point where perhaps we can eliminate, in other words, if I've just cut it from 345 down to 100, I've more than cut it by a factor of 3 as far as the insulators are concerned. Okay, and all of those separation requirements are contained throughout the entire transformer. In other words, each coil has to be separated by that much. All of the conductors within the transformer have to be separated by that much. So you've shrunk it down to about a third of the size of a major 345 kV line. Now, on the end, if I'm an industrial user or a small commercial user, I might be using 480 volt. So let's suppose I've got a transformer there that's taking 100,000 volts and taking it down to 480 volt. And again, we're just supposition here. Now, on the other end, I've got what's known as switchgear, or what they call a switchboard. Okay, and the switchboard is nothing more than a bunch of higher voltage breakers that are capable of handling higher currents. All right, because what you're essentially going to do now is you're going to take them from high voltage, high current to a lower voltage, lower current type distribution. The switchgear is intended to handle the highest voltages and also the highest currents. Now, for example, a 480 volt switchgear would have probably breakers, 2 sets of breakers, could even be 3 sizes of breakers. They could handle up to 3,000 amps, typical 1,600 amps, and maybe 600 or 800 amps, depending upon the manufacturer of the different breakers. So you've got different compartment sizes, okay? And now we're looking at the switchboard or the switchgear. And again, you're talking fairly large breakers. If you look at the size of the compartment, you can get a feel for the difference in breaker sizes. For example, the one on the bottom left might be, for example, a 1,600 amp breaker, where the ones further to the right might be for 600 or 800 amp breakers. All right. Now, that doesn't mean that those are the only sizes you can get them at, because you basically, when you have that size of a breaker, they're adjustable for the current. All right. So, for example, normally those size breakers will have CTs. Okay, so what is a CT? We're going to learn about that in a little bit. But the bottom line is it takes the line current that you were trying to measure and reduces it down through a transformer, but instead of it being a voltage transformer, it's a current transformer. So you have one conductor typically passing through it, and then a number of wraps, and you'll get a typical output of it is going to be, say, 0 to 5 amps. So if I've got, let's say, 100 amps, that would be a 20-to-1 ratio. So I'd have 20 turns on that transformer. If it was 1,000 amps, okay, so now I'm looking at 200 turns inside there. Okay, so the CT is used then to reduce the current down, and I can use that, and they have settings because a lot of them have solid state trip devices, and you can set them up for different current settings. Let's suppose a 600 frame breaker. You could set it for anywhere between, say, 100 amps and 600 amps. Infinitely changeable in between. All right, now, so that's going to be your substation that you're coming into, and this is your main power distribution point coming out of, off of the transmission or sub-transmission. All right, so you came off of a transformer, you came off of the sub-transmission, You came to your primary switchgear, and that is where you're breaking the primary voltage. You go to the transformer, you step it down to whatever the voltage is you want, which in this case we are calling 480. And coming off of there now you have a number of breakers that you can distribute that to different other places along the line. So if we move down, okay, let's look up here at the top. All right, these are important things to realize. Now, when we went into that switchgear, the primary switchgear, all right, that's what's called the service entrance. Now, think of this as a residential. Your service entrance is what is coming out of the meter, okay? It's providing your feed to the house.
The main line coming into the house.
Okay, but it typically comes in through a meter. Now, this gear, for example, that we were just looking at, probably has a meter built into it. So it's got the ability to meter the electricity that's being used. Now, keep in mind, that's what they call service entrance. From there, you have coming off different breakers are feeding different distribution points. Some of these might be 480, like a distribution panel might be considered a 480 volt, so it's going and feeding loads that are 480 or 277. And then we've got lighting panels, which could also be 480, 277, or they might go through a transformer to knock the power down to, for example, 120, 208. And down here, you see a motor control center. Now, motor control center is where you've got basically what we've been talking about most of the class so far, excuse me, is the controls associated with the motor. Typically, they're going to be in a cubicle, okay, which could measure anywhere from about 12 inches tall up to, depending upon the size of the equipment that you've got inside there. I've seen them up to about 3 feet tall or even taller. I've seen them take an entire compartment. Now, typical MCC or switchgear are about 8 feet high, okay? So if I've got a stack, for example, which is what I call a row of, or perhaps a column of cubicles, I might have the incoming feed to that might end up being 24 inches. And then depending upon what I'm feeding from there on out would determine the size of each compartment. Like I say, some could be as small as 12. For example, if I've got a simple breaker that's feeding a subsequent load and there's no starter or other relays associated with it, to the point that I might be feeding, say, a size 1 starter, which might take an 18-inch. A reversing one, in other words, is something that has to change directions, okay, typically has 2 contactors associated with it, a little more room. So that might take up, 18, 24 inches just for a size 1, okay, and let's suppose you get up to a size 4. Well, a size 4, 5, they start taking up some room. And it's not unusual for really big loads that they might take up to, for example, an entire stack, which is 8 feet. But keep in mind, in that 8 feet, there's also a wireway on the bottom, and there's a wireway on the top. In other words, a way to get your cables distributed where they need to go into different columns as we're going along. So a motor control center therefore has a bunch of motor controls, okay? And there could be 20, 30 motor controllers within that motor control center. There could also be a distribution panel as part of it. They might have a transformer in there where they're taking it from the 480 volt, transforming it down to 120, and put a 120 distribution in there. So there's lots of ways to go about it. Now, back into, okay, so we've got feeders that are feeding all them, because again, they're going from a breaker or fuse disconnect or whatever to another fused or breakered panel. Okay, and all of those are considered feeders until you get to the point where you're heading out to your individual loads. At that point, they're considered branch circuits. Okay, why is this terminology important? Because the National Electric Code has certain rules associated with each classification for service entrance, for feeders, and for branch circuits. And they're very different depending upon. So you need to be familiar with the terms and realize when you're doing work what it is, whether it's a branch circuit, whether it's a feeder, whether it's a service entrance. All right? So with that in mind, and we talked a little bit about power losses, so I'm not going to go into that. Okay. Obviously, you need a way to get power, to get your wiring from one place to another. You need something to protect it. Typically, conduits are used, depending upon whether it's commercial or industrial. In commercial, you may end up using EMT, which is electrometallic tubing. In industrial, again, they're allowed to use electrometallic tubing, but for the most part, you're going to get involved with what they call rigid conduits. So it's more like a pipe, in as much as, yes, you can bend them, but you need a little heavier equipment to bend a rigid conduit than you do a electrometallic tubing. Okay, and you also have where you have a lot of circuits that are going to go and perhaps fall out along the way. For example, let's suppose you've got workstations in a machine shop, and you're going to have cables that are going from one end of the machine shop to the other and maybe running to the other side of it and then back again. Well, rather than do a bank of 100 conduits, it might be wiser to use what they call a cable tray. Cable tray can be 6 inches wide, and typically they're about 6 inches deep. You can get them shorter, but 6 inches is about the typical size you're going to see. You can get them up to 3 feet wide, and it handles a lot of cables. It makes it much easier to pull cables, and also you can separate, for example, if you're separating circuits, typically they separate them into 3 classifications, which is what? Power, control, and instrumentation. So for purposes of this discussion, I would consider power being the 480 volt. Okay, control is usually 120 volt. Okay, but it could be lower, it could be 24 volt. Depends upon the place, the philosophy of the manufacturer and the architect that's designing it. But it's not unusual to use 120 volts, very typical in fact. And instrumentation, essentially what you're dealing with here is very low voltage, very low current signals that you want to keep separated from power and control, because we learned that current tends to induce voltages, flow of current induces voltages in other cables. Well, with instrumentation, what you're doing there, since you have very low level signals, it's not going to take much interference or much induced voltage to basically make the signal meaningless. So typically what they do there is they use shielded cable, and the shield basically, you've seen them before, where it's a aluminum wrapped around, or it could be a braided copper shield that goes around the conductors on the inside. There's many, many different schemes that I've seen and used. They're very effective at basically shielding the inner conductors from outside sources of interference. All right, so typically they have a power control and instrumentation cabling system, and that usually is kept throughout the entire plant. All right, we're talking, moving down there. Once you get into, feeders, some of those feeders may be used to feed here's a 480 volt, some different types of 480 volt equipment. You might have a UPS or an inverter supplied system to feed some of your more sensitive instrumentation. Okay, and let's look at what else we got there. Switchgear and paddle boards. Okay, switchgear is generally the higher current, higher voltage type stuff. As you're getting to your paddle boards, again, you're going down perhaps at the same voltage, but down in currents, okay? And as you're doing that, you're getting closer and closer to the loads. And you can have branch circuits coming off anywhere along the way. Okay, so just because it's coming off of a switchgear doesn't mean it can't be a branch circuit. It could be a feeder if it's feeding another distribution point. If it's feeding an actual load, then it would be considered a branch circuit from that panel. All right, now if we look at this, you can notice that in this case, the secondary winding of a transformer, or this could be a motor, depending upon what you've got going there, okay, is the benefit of using, let's look up at this one because it's actually showing a distribution type thing. The benefit of using a Y connection is the fact that your phase and your phase to phase and phase to grounds are related by square root of 3. So for example, I can come off a distribution panel down here, okay, and if I want, I can take a 3-phase load off. I can take a single phase load off. So let's call